Awesome. So we're just back from the lunch, I understand, so everybody's feeling a bit heavy, so I'll try to make it super quick. Yeah, my name is Odysseas. I'm the founder and CEO of Phylax Systems. We're doing security. And in this talk, I want to talk a bit about how we are using Solidity in a very different way in our protocol, in our system. I think Solidity is, it's a language that everybody knows, and this allows us to use it in ways that is not just only for, EVM development. So obviously, Solidity was introduced, by Ethereum as a language for development. It's a JavaScript-like. And then dApp tools take it a step further and said, actually, why not use the same language to test, right? Why do I need to learn JavaScript? Nobody likes JavaScript. That's a fact. So yeah, let's use Solidity for testing, right? And then obviously Foundry, Halmos, they took it a bit further. Foundry made fuzzing and invariant testing, more powerful. Halmos implemented a version, like a form, if you want, of invariant testing, of formal verification. And of course, now we have Phylax, which we introduce Solidity to enforce invariance and runtime. So what are invariants? I want to deconstruct this a bit. So we are using Solidity to allow the developer to express an invariant, something that should be true about our system always. And then we enforce that at runtime, right? And runtime, we mean whenever a transaction interacts with our protocol. Who knows what this is? This piece of code. Who can read it and tell me what this is? Anyone? Someone? What is it? Exactly. It's a fork test, right? A fork test, for those who don't know, is basically a type of test that dApp tools introduced and Foundry made famous. And basically, it allows us to run a test against the state from a live blockchain, basically, right? It's send the current state or historical state instead of just having an empty state where I have to set up my own environment. So this is how you run it. You say fork test, you give an RPC, you say for which block number you want to run it, and then it will populate the state from that block number, and it will run your code and see what happens. So what if we run this command, but we run it on every new block, right? So we do a fork test now, but we run it on every block. Effectively, what we've made is a monitoring solution. We have our Foundry, our fork test suite. We have some code that checks our protocol against some live state. And now we do it for every state, right? We do it for every block. Effectively, we built a very, the poor man's version of a monitoring solution. The problem is that alerts are lame. You can see, oh, nice, my protocol was hacked, but you only see it after it was hacked, right? With great DevX, though, which thanks to Solidity. So now we say, OK, let's take the same concept of that of a fork test and then run it during the state transition function, right? Imagine we have a system, an EVM chain, where we have a transaction, we have some state, it enters the EVM, that produces another state, obviously, a result, and then we feed all of that into a new EVM that runs a fork test, a Foundry fork test for that state transition, right? Imagine you could write and execute a Foundry fork test for every state transition that touches your protocol, right? That would be amazing. And that's what we've done. So in our system, how we use it, we allow developers to write what we call assertions, which are the fork tests. And then they can associate it with their contracts, right? They say, for this contract and this contract, I want to have these fork tests. And whenever my contract makes a state transition because a transaction touched it, I want to execute the fork test and make sure that the state transition was valid. So before, without this system, we have the transaction, it touches some contracts, we execute the contracts, and then we have a result. Now, for the computation to be valid, we take the transaction, it interacts with some contracts, And then also we have to run the fork tests, the assertions for these contracts. And only then do we say that the state transition is valid. In the very simple terms, this is effectively what we build and how we use Solidity in this very different way. So an interesting attribute, which basically we inherit from, from the fork test, is that these assertions, these computations are atomic and read-only, right? They just read state, and either they succeed or they don't, which means that we can parallelize them very aggressively. They also express the what and not the how, right? So you can imagine it as a lazily executed fast test, right? Where instead of having random inputs being generated by a system, the random inputs are actually the transactions of users, right? Same thing. We have a fast test that is executed on runtime, effectively, with inputs generated by the users themselves. So the developer doesn't need to find or think about how the code can break. Obviously, it's important. But even if they miss something, if they have encoded the property in these fast tests or fork tests, in these property tests, the transaction will not be added to the block during the state transition. So how does this system work? Very briefly. So there is an on-chain registry or smart contracts, and we allow then a team to go there, and they can define them rules, these assertions. And then whenever a transaction goes to the network, there is a sidecar to the validator node. So the network has to adopt it. And then the sidecar will take the transaction, execute it, and then we'll see whether the transaction interacts with any protocol that has defined these assertions, these rules. And it will execute this. And if the transaction violates these rules, if the fork test fails, then the transaction is dropped and not being added to the block. If it passes, it's added to the block. So what we get here is basically hack prevention, right? Basically, this is almost a step-level improvement in security where you will actually catch the hack during the state transition. If you define your properties correctly, it's impossible to be hacked. And another nice thing about reusing Solidity here is that it's a system that's very easy to use, right? You can just take your mental models, you write Foundry, you know that, you know your properties of your system, and you can use it. Versus other approaches that require a lot of context that are complicated, right? And part of why we adopted this Foundry style mentality, and we basically do the fork test and we execute it on the state transition, even if it's not the most performant or most effective, it is the easiest. And also, it is the most powerful. So this is an example from the balancer. So this is a part of the code of this fork test, this off-chain Solidity code that runs by the sidecar. We have some new precompiles. So in this particular precompile, we have taken all the calls made in the transaction. We have filtered them for the calls we care about, the calls that would change this K factor. And then we fork between the state of these calls. And basically what we say is that the K factor should not change more than 3x in a single transaction, in a single call, basically, right? If that happens, then we say, OK, obviously this is wrong. It's not expected of the protocol. It's not expected for any call to modify the K factor more than that, and it should fail. This is a very simple example. The interesting thing here is that when we created this code here, we didn't know exactly what was the root cause of the hack. And that was important for us because a core thesis here is that we don't need to know. We just need to identify the property. And I'm sure someone will say, oh, Odysseus, that's a heuristic. That's not a property, right? That's not an invariant. That's true. In this example, we found a heuristic. But the beautiful thing here is that either works. We have examples with protocols where we define these properties in Solidity, which are actually invariants. We define these properties that should never be broken. But also for some other cases, we can use heuristics, right? based of the historical performance or historical context of the protocol. We can understand what are the heuristics and create, some rational thresholds where we say, okay, if something goes beyond that, well, something is up. Someone is trying to do something weird with my system, and I don't want to know anything about that. I mean, I want to know about it, and I just don't want to allow it to happen. So that's it. Thank you for working with me on how we use Solidity in a very weird, yet very powerful way. Here's my social. I'm down to chat. Thank you so much.
Thank you so much, Odysseas. The session QR code for questions is up on the screen. I don't have any questions as of yet, but do we have any more questions from the audience for Odysseas? Yes, I can bring the mic to you quickly.
Are these sidecar invariants that you run public or private? So if I'm a potential attacker, can I just simulate my attack transaction against your invariants? And if I know them already, I'm just, in the balancer case, I'm going to make that K value 2.99 instead of 3 and just run 10 transactions instead of 1.
Yeah, so you've gotten a very interesting edge case, right? So we think there is no reason for these invariants to be either public or private. It can be none. It can be both in a system. We developed in a public way because we think that the user should know when the properties of the system they interact with change, right? Because these invariants, this code, these assertions is Turing complete. So the protocol can do anything. But the thing is, that the interesting thing that you mentioned that is, in the case of a heuristic, indeed here we would lose, there is information leakage here. We tell the hacker how to go around the heuristic. So indeed here, probably the heuristic should be a bit different, maybe much lower, so that the hacker, it gives time to the team to do precautionary measures. But if it's an invariant, then there is no signal to be leaked. Like if I tell you the invariant, of Aave, of a protocol, right? That doesn't give you any signal, any information on how to actually break that invariant. I can tell you right now that, your protocol should not be upgraded when you sleep. I don't know how that can happen. I don't know if your private key is leaked, or there's a Trojan horse on your computer, or, you've hired North Korean, people or whatever, right? So yeah, that's very interesting. So heuristic indeed, but for invariants, if you define it correctly, then indeed telling you an invariant gives you no information, but per definition of how to break this invariant.
Another question for you. For dropping a transaction that fails test, does validator need to sign up? What if a hacker waits for a validator who will not drop it?
Yeah, so here we go into the kind of worms of the architecture because it's a very different approach. So when we think about validators and L1s, the approach we will most probably follow is what we call of application-specific sequencing. So effectively, you say, I restrict the number of validators that can interact with me, that can sequence my transactions to a specific set that follow this, have adopted this solution because I want to exchange basically liveness for security, right? That's the trade-off you're doing. For L2s, where we're focusing right now, and we're seeing a lot of interest, obviously you have only one party to convince, and they have a lot of incentive to be convinced because they want to attract institutional capital that is very risk-averse, and something like that is a very familiar architecture that you can find it in the New York Stock Exchange, you can find it basically in any exchange and any TradFi, this type of circuit breakers that protect the system from something bad. And especially in a blockchain system where there is no recourse, once something happens, it happened. These things are more valuable.
And one final question. Invariants can be in between transaction or in between opcodes. Which ones are more important, and can you capture both What if you don't know the contract implementation?
Right now, we implement invariants between transactions and calls. We want to support between multiple blocks in the past. So being able to fork a few blocks in the past. For opcodes, this sounds difficult to implement, difficult to audit, and I'm not sure how much detail you get. Maybe there is value. It's not something we have really explored. Thank you for the feedback request.
Thank you so much for answering the questions and for the amazing talk. Please give it up for Odysseas.
Thank you, everyone.